Hi, my name is Bradley Strunk, and I will be talking about electric generators. The purpose of this instruction is to teach you about the electrical and mechanical systems and operations of generators and how they relate to electromagnetics. Generators. When people think about generators, they often think about power plant and standalone generators. Power plant generators often have a turbine which is spun by an external force and creates electrical power. Standalone generators, such as this one seen here, are often engine run. Engines require fuel and air to create combustion. The fuel could be propane, gas, or diesel. And the mixture of these two goes into these combustion cylindrical chambers where compression occurs, heat is added, and combustion ultimately happens. This combustion then turns a crankshaft, which turns a flywheel, and ultimately turns the rotor. The rotor is the rotational part of the generator. The stator is the stationary part. Now with these two components, you need one of them to be a magnet and one of them to be a coil of wire. It doesn't matter which one's spinning, but it matters that you have both of them, one spinning and one not. Now with these mechanical systems, you need a lot of mechanical maintenance as there's a lot of moving parts. The electrical system. So in this diagram, this shaft is acting as the rotor with the electromagnet attached to it, and the conductor is the stator with the coil of wire. Most electric generators have a balanced three-phase AC system. In the United States, you'll see them having 60 hertz, which is the frequency, or 50 hertz over in places like Europe. Two-phase power is possible with these generator systems, where if you have each of these phases having a certain amount of voltage, but you want more, you can attach them together and create a two-phase system. Now with this two-phase system, you'll get an upgraded amount of voltage, but you will have voltage loss, such as having two 120 volt phases, bringing them together and getting 208 volts. Rotation of the rotor and the stationary stator cause opposing fields, which enables the power production ultimately. Specifications can vary from generator to generator, and you can often find these on the info plate, such as the kilowatt or even megawatt production and the fuel type. AC has a lot less loss than DC, so it is often kept in the AC electrical form when it gets transmitted across transmission lines and when it's on distribution lines, until it gets to the customer where it gets inverted or converted to DC if needed. Now, how is this possible? This is where Faraday's law comes in. Faraday's law of induction explains how a changing magnetic field induces an electric voltage in a conductor driving electric current. This is the equation here. Delta V being the EMF or the voltage. The IB being the magnetic flux. And this is calculated by multiplying the field by the area and then the cosine of the angle between the field and the normal of the loop. Now the d over dt is the rate of change over time of the magnetic flux, and the negative is just the natural induced EMF opposition to the magnetic flux change. So this is how we calculate the voltage that gets applied to our conductor. Now we're putting this all together. In electric generators, mechanical energy is converted to electrical energy via Faraday's law, which we just talked about. What you need is magnets, metal, and motion. As the rotor turns, magnetic flux changes over time. The EMF induced in the coil drives current through the coil, creating electrical power. Now, the voltage generator and ultimately the power depends on many things, such as the magnetic flux changes or the RPM, such as how fast the rotor is spinning, the strength of the magnets, and the amount of loops in the coil of wire. Conclusion. My name is Bradley Strunk. I've taught you the basics of electric generators. Some key points I want you to remember are electrical power production requires magnets, metal, and motion. Electric generators turn mechanical motion into electrical power, and Faraday's law allows the production of electricity through opposing magnetic fields. Here's me in the military with an over 1 megawatt generator, so that's something cool that I thought I would share. Now, the importance of electric generators in the future. Electricity is needed for all the technology we have today and has been needed for the innovations we've had for a while now. And so for the foreseeable future, whether it's a main source of energy or it's a backup, electric generators will always be needed for the foreseeable future. Now, here's a list of my works cited. I got a lot of information from these sources. I would also like to say I've had many internships in the power field, and I am in the career field of electrical power production through the Air Force, so I know quite a bit myself. Thank you for your time, and I hope you learned a lot. Thank you.